Welcome to the libcurl video tutorial episode Receive Data. So I'm here again. We have the text editor on the right, the terminal in the middle, and myself up in the corner. And today we're going to look into receiving data with libcurl in your little application. And what you see on the screen here is the pretty much what we ended up with in the simplest episode. It's a very basic libcurl using client that just receives, well, it makes a transfer, it gets the data from the https://example.com website. It makes it perform, and it sends everything to stdout because it doesn't set up any other default. But most people or most users, most applications probably think sending the data to stdout is not the perfect way to do it. So we are going to take a look into how the options we have to store the data differently or receive the data somewhere else than sending it to stdout. So I'm going to dive right in. First, I'm going to show you here in the terminal a little hint. If you install the documentation package on your Linux distro, you'll get the man pages, and we have man pages for every libcurl option. Well, all the options to curl easy setup and to a few other of the libcurl functions. So you can do this man curl up the right function. And why right? Because the naming here comes from this sort of the aspect of what we tell curl to use instead. So curl originally uses a write function internally to send the data somewhere. When it wants to store it, it writes. So we can set up another write function. So here's the man page for the curl up the write function option. So it sets up a callback, and as you can see, there's a lot of documentation here. So I would advise you to read all the tiny details if you want to figure out exactly how it works. But the gist of it is that it introduces, or it points out a callback that it sends all the data, that libcurl will send all the data to. So if we would copy, if we would create, we could create a callback like this, maybe. Here's I'm just copying the prototype here to make sure that we get the correct arguments and the correct data types. So we make it static because that is a nice way to do it, since it's not going to be used anywhere else. So this is the right callback. Okay, and we can tell curl to use this right callback by setting the option curl opt write function, and we point out our callback with it there. Okay, so now when it gets do this transfer, it'll call this write callback for all data that it receives, and it will call this function over and over until the transfer is done. And what do we do in this function with this data? First, one interesting thing to note, and is mentioned in this documentation on the left side here, is that the data comes in this pointer, the first one, and this last one called user data here in my program, that's set with another option to libcurl called write data. So we can pass a pointer from our function here into our callback by using that. Sometimes we call that user p in some other context, so let's call it that, and we could call this contents because that's the actual contents that arrive into the function. So, and this function, the callback function, we should always return the number of bytes we took care of. So otherwise libcurl thinks something wrong happened, it'll abort the transfer, but we don't want that. So we know that the size multiplied with the number of members, or whatever it's called, this is actually copy of how the fwrite function works. So these arguments are copied once upon a time from the fwrite function. That's why they're using this it uses these funny names. So we return this. It says, yeah, we took care of all the bytes. Yeah, sure. So, and we can, well, we don't use anything at all there right now. So if we build that and we run it, what happens, do you think? Bam. Well, what happened here? We asked for a transfer. We sent all the data to the right callback function. The right callback function does nothing and says it takes care of everything. So yeah, it worked, but the data just vanished into thin air. Yeah, right. So we can, if we want to see that it actually works as well, we can got %d bytes perhaps. I mean, size times nmemb. I'm typecasting it so that I can actually use %d properly. Boom. Okay. We got everything in one callback, it says. Well, yeah, that's that might be if we would do curl and on the command line, just as a comparison, we would get that and we would type it and to the word count code program, and it says, yeah, 1256 bytes. So that's the number of bytes we should get. So it seems sensible to, but okay, we don't want to just throw it away. What do we do with the data? We want to store it maybe in memory. That's a popular demand. Many wants to do that. There's an excellent example in the libcurl documentation called getinmemory.c. So let's try to mimic that, right? We want to receive all the data into a memory block, and we store it there. And yeah, what do we do with it? Maybe we could print. Print it seems point. Okay. First, we create a little struct so that we can deal with this somehow. Size t size. So we just have a little struct, and if we, this is just so that we have some data that we can pass into the callback, and so we can get it from the function into the callback, and after the transfer is done, we know the data or can deal with it somehow. So we here in the beginning of the function we declare it here, call it here's the memory chunk, right, and we should initialize it to something, right? We set the memory to null, and there is nothing because we don't have any pointer to it, and the size is 0 bytes big. Nobody has sent us anything. Okay, and here I'm just going to duplicate that because it's going to be similar. So I pass in a pointer to my chunk variable, to the struct right here, with using the right data option. That means that it'll send a pointer here to this chunk in this user p variable into the callback. So in the callback, we can do like this. First, we can, for example, take care that the real size that we get is actually them multiplied by each other. So let's do that. And we want to get a pointer to our chunk struct that we passed in. We passed a chunk there, we call it via the user p, and we get it out again, and here we call it mem. I'm not calling it chunk because it makes it too confusing. So okay, so here we get a pointer back to that struct, and we know that the struct contains the memory is null and size is 0 from the beginning. So we can do like this. We reallocate the size that we keep to store the data in, because we know that realloc handles a null pointer from the beginning properly. It'll just behave like a plain malloc if we do like this. So mem size plus the real size, because we want to add any previous size, because if we get called multiple times we want to keep expanding. So, and let's add one so that we can add a terminating 0, because this callback doesn't get any it gets the data and no terminating 0. We can't presume anything other than that. And of course, if this returns a null, then we failed and we return an error. And if we return 0 here, that's not the number of bytes we got to deal with, so it'll return a different value than real size, and that'll signal an error to libcurl, and it'll abort the transfer. So we store then the memory store that the new one we got. We store the new size too, right? The size we add real size, not realize. Did I call it realize? No. Real, there I call it realize. Real size. It's okay. Append to the size because we got more data now. We wanted I added this one to make sure that we can 0 terminate the data. So we can 0 terminate the data. If this is strictly speaking not necessary, but sometimes it's convenient because people who work with C tend to sometimes forget and think that the data is 0 terminated. So okay, but we don't take care of the data here. We realloc, get the new pointer, we add the data, but we never copied the data. So let's copy the data as well, because the data comes in this contents pointer. So we can copy the data, and we copy the data. Where do we put it? We put it at the mem size position, because that's the previous data size. And we copy it from contents, and we copy real size number of bytes. Bam. So now this is the number of bytes we get into the callback. We figure out the pointer to our struct. We realloc the size of the data we want to store, receive the data in. So we store the new pointer, we copy the data onto our realloced buffer, we add the just keep track of how many bytes we have here, and we 0 terminate, and we return and tell libcurl we handle all the bytes. So if we do this now, what happens? Well, we lack a few. So see, we don't include standardlib.h, stdlib.h, and we don't include string.h. So maybe we should fix that, and then we can try again. We don't want any warnings. So, and what happens if we run this? Boom, nothing. Well, in this case, we weren't really supposed to see anything, right? Because now the write callback gets called for all the data. It gets data, it reallocs for every invoke and stores it, and everything ends up fine and dandy, right? So in the end, if we would, well, if there's no error, right? Else, maybe we could use braces like this, and you can have your arguments about my coding style or indentation style, or you can do it differently. But okay, there was no error. Then here, printf, we got bytes. We got %d bytes, and again, it's about what the data type is. So we got to our callback. So what do we get? How many bytes do we get here? Mem size. We rebuild it. What did I do wrong? It's not mem in here. That was what this was called in the callback. It's called chunk here, and it's not a pointer. It's a struct in here. So chunk size starts with 0 and it gets added in the callback. Added to. Make, run it again. Boom, 1256 bytes in our callback. And at this point, in memory, we could just to illustrate, do like this, chunk memory. There, that's the pointer then to the memory buffer that contains our 1256 bytes of data. So what do we do with that? We of course free it when we're done with it, because we don't want to leak the memory. And when we've freed the chunk memory that we reallocated, we also free our transfer handle as usual, and we do the regular global cleanup. So in here, if we wanted to deal with the data somehow, like this looks like this. So it says domain somewhere in that. We're going to look for domain. So if we domain, and we can use stir, you remember the man page. So we want to look for what the haystack happens to be the chunk memory. Here's the pointer to all the contents we got, and we want to look for domain, or was it with a capital D? It was with a capital D, but it's also with a lowercase. So let's do the lowercase. Printf found domain at index. Domain is now much bigger than the chunk memory. Yes, and this is, I mean, why do I search for domain in there? I don't have to search for domain. I'm just showing that it is actually data that we can play with. So what do you want to do with the data? Of course, you have some purpose when you write a program that does something. So this is how you receive it with a right callback. Everything is fine. You can invent your own callback code here and do whatever you think is fun. And of course, you can, I would advise that this realloc thing is done in a smarter way. Don't just add the real size sort of. If you want to do this many times, maybe double the memory in all every time you need to, so that you can reduce the number of reallocs and just do a few instead of doing them every time now, because it might become quite a large number of callbacks if you do this with a large file. But then of course, if you do this with a large file, you might not want to keep it all in memory like this. You want to store it to a file instead, and then you can do that instead. This is just how to receive data. I'm going to come back with more examples and more useful things to do with libcurl in other episodes. See you around.